We next introduce Professors Elsa Olivetti from Material Science and Engineering and Robert Jaffe from Physics. And they're going to address some of the materials issues, which are, I think, quite interesting and compelling. And we've already seen questions about that in the Q&A section. They're gonna tag team on this. You can start with Elsa's going to begin, and then go to Bob, and then back to Elsa, and look forward to a lively discussion. Elsa. Elsa, I think you need to unmute, and then you're ready to go.
Sorry, my
Great.
mouse won't cooperate with my with my Zoom. Is that all okay there?
You're good.
Excellent,
Full screen.
excellent.
Thank you.
See if I can get the mouse to cooperate. Thank you so much, Bob, and it was great to hear the previous presentation and how well it links to what we're going to talk about today. So we're going to dig into some of the challenges around materials around the energy storage topic, and I'm going to start with a couple of high-level thoughts. Many of the technologies that we consider really critical to the transition to a low carbon economy rely on key materials, and gaps in the availability of those materials may inhibit that transition. And one thing that I'll point out in a bit of this overview at the beginning and the end is that there's often trade-offs in this upstream impact associated with those materials, and that there's a set of tensions that introduces, and we need to think, in cross-disciplinary ways in order to think about that. So in this session, what Bob and I are going to do is I'll give a little bit of the overview, sort of context around what I mean by this assertion, and then Bob will dig into detail on the study itself and what we learned, and then I'll come back up to some big picture at the end. So what I mean by this first assertion is that the rapid deployment of energy transition technologies needed that we just heard about really have a significant implication around an increase of demand for minerals. And this is shown in two ways on the slide. One, on the left side, in a per unit basis, this assertion I made about that we're going to have a mineral intensive future is shown by the juxtaposition for each of these technologies in transportation and power generation, thinking about the incumbent, which is below the red line in each of my categories there, conventional car and coal and natural gas, versus the materials required in a low carbon setting, so an electric car versus, and then wind and solar, et cetera. And you just see the stronger rainbow of colors associated with the newer technologies or the lower carbon technologies as compared to the incumbents. And so that in and of itself is this indicator on a per unit basis, the requirements are going to be stronger, and the deployment of these technologies implies a significant increase in demand. And that's shown as an example on the right-hand side. And this is just showing an example across minerals of interest, graphite and lithium and cobalt being the first three there in that bar chart, in the projected annual mineral demand in percentage of 2018 demand under a 2-degree scenario for warming from only energy technologies. And so we see really significant increases in minerals like graphite, lithium, and cobalt that we'll dig into in more detail. To meet these energy storage technologies, and even demand for base minerals like aluminum and copper may be smaller percentage wise, but the absolute production figures are quite staggering. And so because of this challenge, we need to think about what the implications for materials are. What this means is, a couple of different things. One is a different geographic distribution of our supply chains, and this is shown in these plots. Extraction based on geography is shown on the left, and processing based on geography is shown on the right-hand plot there. And you see in the different colored bars there, the share of the top 3 producing countries in production of fossil fuels of selected minerals. And again, I'm using this red line to divide incumbent this time on the upper part of my red line, and then the minerals that are relevant for the technologies of interest on the bottom line. And we see again, a shift in color, so a shift in geographic supply chain, and also differential kinds of concentration. The story on the right in terms of processing is very much a China story, as we all know well, in copper, nickel, cobalt, lithium, and rare earths, in terms of the share of production that's dominated by those regions. And so that means new energy trade patterns, new dependencies on geopolitical considerations into play that we read about in the popular press often, in the newspaper often, but it's really underscored as we continue this necessary transition, the degree of dependence on those supply chains. So we've got increasing intensity of minerals needs, how that shifts supply chains, and we have to reconcile that with also temporal challenges, both in that was reflected in the conversation we just had around different kinds of technologies and how will they be deployed. But as we think in this session about kind of thinking upstream in terms of what's that going to mean in terms of extraction, there's another temporal challenge, not just in demand, but also in supply. As we know, it takes time to build new mining projects, to prospect them, plan, fund, and permit them in terms of discovery, in terms of feasibility, in terms of permitting. And the global average lead times based on some top mining projects are shown on this slide was about 18 years. And so if you think about the ways in which we need to transition from a decarbonation perspective, that is on that order of timeline. And so again, these sort of temporal challenges of reconciling what it takes to build a new project, that's going to vary by mineral, as it's shown on the bottom there, in terms of lithium in different geographies and nickel according to different extraction, and then copper as well. That the reconciling these temporal challenges are something else we have to think about, and really kind of one of the main cruxes of the message that we want to send here. The materials availability question is not necessarily one around running out. It's a question on, can we meet demand at the temporal scale that we need in order to accelerate, in order to meet the necessary transitions. And really why we care about materials availability in this sense and potential supply chain constraints is this temporal challenge, and is there impact on price? So again, as I said, it's not necessarily about running out. It's about risk and the influence of that risk on price. And there are a couple different ways we like to think about this. On the left-hand side of this is a plot published by Professor Cheng, who you all just heard from, and also Professor Bill Green at MIT in chemical engineering. And the point of this plot is to show that materials costs start to set practical lower bounds on the price for some of these technologies. And so here we're showing in the blue curve there is a learning curve. The red part is historic and the blue part is projected in time, and we start to see, as we have learning in the manufacturing associated with batteries in this case, we start to reach this floor on the active battery material costs and then subsequently the mineral costs. So volatility in those costs based on the challenges or perceived challenges of meeting supply at the scale that's needed means that we start to be subject to those materials costs, and that they may influence our ability to implement new technologies. And the kind of more qualitative way to think about this point is that when we're talking about materials availability or materials criticality, we're not talking about scarcity definitionally. We're talking about things like market imperfections, the ways a material is mined, if it's mined as a co or byproduct of another mineral, which we'll get into in more detail in a bit, how substitutable that technology is, how substitutable a material is within that technology, and so on. And so taking all these factors into consideration is what we mean by this risk associated with that, and is a particular risk based on a resilient supply chain deemed too high by a decision maker, both in a policy context or in a manufacturing context, that would limit our ability to scale technologies or scale a transition at the rate we would need to. So that's the baseline in our starting point of how we want to talk about materials availability. So I'm going to turn things over to Bob now.
Good. With a little bit of luck, you can see my screen. I'm going to thank you very much, Elsa. I'm going to talk about our study's observations about the particular critical minerals that are used in electrochemical energy technologies. As has already been mentioned, all energy storage technologies are material intensive, Requirements for materials rise in direct proportion to the amount of energy that's stored. For many of these storage technologies that are discussed in the MIGHTY report, the energy storage media are cheap and abundant materials such as water or thermal oil, rocks, or molten salt. Batteries, on the other hand, require electrochemically active materials that are not necessarily earth abundant and may be subject to availability fluctuations and price volatility. Therefore, materials are particularly critical for the future growth of battery energy storage. I want to say some words about scale. The criticality depends on the scale of battery deployment. In Chapter 6 of the report, we estimate that the total energy storage capacity necessary to fully decarbonize the US electricity sector might approach 100 terawatt hours by 2050. On the other hand, further demand for batteries will come from a rapidly expanding adoption of electric vehicles. And still more will arise from the grid storage and electrical vehicle storage, energy storage requirements throughout the rest of the world. Therefore, all these demands will compete for the world's resources of critical materials. So we need to consider more than the US materials demands in this context, but rather the entire world's demands for electrochemical materials. And we believe that it's necessary to consider hundreds, if not thousands, of terawatt hours of demand for electrochemical energy storage. As Yet and Fick have emphasized, the present dominant technologies on the 2020 to 2050 horizon are lithium-ion batteries and redox flow batteries. Lithium-ion batteries, of course, dominate the electric vehicle market. In addition to lithium, as has been mentioned, these batteries employ nickel, cobalt, and manganese in their cathodes and are therefore labeled with this NMC logo on the nickel, manganese, and cobalt molar proportions. The redox flow batteries, which are another promising technology described by Fick, at least in their present form, require vanadium for both their positive and negative electrolytes. Thus, we've identified lithium, cobalt, and nickel, and vanadium as potential materials of concern for expansion of battery technologies. I should note that manganese is a much more abundant material and is not on our list of materials for concern. You can get a first crude look at the scale of material demand as shown in this table, which lists the number of years of current production of these four chemical elements that would be required to deploy 100 terawatt hours of battery storage. As you can see, for lithium-ion batteries, the trend is toward a lower proportion of cobalt and a higher proportion of nickel. That's reflected in the number of years of cobalt and the number of years of nickel production required for 100 terawatt hours of battery storage. It's obvious from this table that these numbers are extremely large compared to any estimate of direct extrapolation of current production over the 30-year period of our study. Also, for 100 terawatt hours of vanadium flow battery production, would require almost 400 years of current production of vanadium. So let me start talking about these by first quoting the findings in the report on materials, which reduce the materials discussion to a single sentence, that the rapid deployment of batteries in the United States and abroad, primarily in electric vehicles and secondarily in grid storage, will require increased production of certain critical battery elements at rates that far exceed historical averages. Constraints on the scaling of the production of these critical elements already exist will likely persist and will have implications for the technology development pathways. To dig deeper into this and to get a more nuanced picture of material requirements of battery storage, we have found it useful to look at a kind of global analysis in terms of a sustained average compound annual growth rate, or CAGR, required to meet a deployment goal by, for example, 2050. These graphs contain a lot of information, and to get a better feel, let's look at one of the graphs more carefully. The assumed integrated deployment by 2050 is shown on the horizontal axis in terawatt hours. The required average compound annual growth rate over that 30-year period from 2020 to 2050 is shown on the vertical axis. Crucial information further is shown as a histogram on the vertical axis, which shows the historical values of the compound annual growth rate for this material averaged over the 20-year periods between 1970 and 2020. The vertical lines on the right show the total battery deployment given the existing chemistries that would be allowed by the present world-known resources in 2020 for the particular element in question. The CAGR, of course, depends on the fraction of the material available to use in batteries and on the composition of the batteries. This information is displayed by the red, blue, and green domains on the graph. The green, red, and blue refer to which fraction, 25%, 50%, or 100%, is available for use in batteries as opposed to competing demands. And the bands of color, which in this case for lithium are rather narrow, show the dependence on the composition of lithium-ion batteries, ranging in this case from 622 proportions to 811 proportions. For example, if 100% of the resources of newly discovered resources of lithium were dedicated toward battery development, of 100 terawatt hours of deployment in 2050, this would require a compound annual growth rate of about 18% averaged over the next 30 years, which is more than twice the compound annual growth rate that has been observed at any time in the previous 50 years history. Let's return then and look at, in light of that, at the cobalt graph. For cobalt, the numbers are similarly challenging. And in this case, the required material for deployment of 100 terawatt hours of lithium, cobalt, manganese, nickel batteries would approach the world's known resources in cobalt at the 100 terawatt deployment level for the 622 composition, and be within a factor of 2 or 3 of the world's resources for the 811 composition. Because the amount of cobalt varies significantly between the two battery compositions, the bands change significantly when we go from 33% to 100% of the deployed cobalt, and also change significantly between the 811 and 622 compositions. The historical CAGRs for cobalt are more wide-ranging than for lithium, but don't exceed 10%. Finally, let's look at nickel and vanadium. In some ways, nickel is the most challenging. The first, because its historical CAGR range is quite narrow. Second, the high demand for use of nickel in stainless steel makes it unrealistic to suppose that a high percentage of new nickel discoveries will be applied to battery technologies. So one's looking more at a number like 25% than anything approaching 100%. And third, the chemistry of nickel is not favorable. Most nickel is produced as ferronickel, which is in fact unsuitable for battery use. Finally, regarding vanadium, which has a rather large distribution of historical CAGRs, the known vanadium resources are just much smaller than the other elements, amounting to well less than 100 terawatt hours of total deployment. So that 100 terawatt hours of deployment of vanadium redox flow batteries by 2050 simply looks out of reach in terms of modern resources, known resources of vanadium. So let me review then the findings of this analysis in a little more detail. The first echoes something that's been said before, that at a higher end of deployment rate, as we considered it, the required rate of increase of production of critical elements that we've identified equals or exceeds historical rates of growth. And this will imply expansion of extraction, processing, that is beneficiation, and refinement well beyond current infrastructure. It also implies that producers should be aware of the appropriate technology for a given application. Space and weight constraints are at a premium for mobile applications, such as electric vehicles, which require high energy densities. And as such, nickel, manganese, cobalt-based lithium-ion batteries would be favored for those applications to obtain the rapid scaling anticipated for electric vehicles. This contrasts with low energy density chemistries, such as lithium iron phosphate, lead acid, or metal-air batteries, which could in fact play a greater role in stationary battery storage. Of course, we recommend research and development on these battery technologies that make use of earth-abundant materials to avoid dependence on these critical materials. And note that neither weight nor round-trip efficiency is as great a constraint on stationary grid storage as it is on mobile electric vehicle storage. Given the level of significant scaling that's required, it's imperative to more effectively manage resource extraction to include the concerns of externalities such as environmental and social implications of mining and beneficiation. Let me make comments on some of the individual elements before passing the mic back to Elsa. Our conclusions on lithium are perhaps the most optimistic among the critical battery materials. Lithium production has grown rapidly in response to demand for device and electric vehicle batteries, demonstrating elasticity in lithium supply. Furthermore, over 70% of lithium production at the present time is already directed toward batteries. Also, new extraction methods promise more efficient and economic extraction of lithium from brine, which is the presently dominant pathway, with fewer externalities than the evaporation method presently used. And hard rock mining of spodumene from pegmatites has emerged as an important component of lithium production. And in the future, extraction from lithium-rich clays is also possible. Nevertheless, even in these so-called earth-abundant technologies like lithium iron phosphate, lithium is still required as a critical material. Regarding cobalt, many problems with cobalt are well known. Cobalt production is highly concentrated in the Democratic Republic of the Congo, which now produces over 70% of cobalt at the present time, Australia and Russia being distant seconds to the DRC. Furthermore, processing of cobalt ores is highly concentrated in China at roughly 70%. In addition, a significant fraction of cobalt production in the DRC takes place in small-scale artisanal efforts, which typically have greater negative social and environmental impacts. Also, cobalt is primarily produced as a byproduct or co-product with copper or nickel, making cobalt supply relatively inelastic in response to demand due to the dominance of the primary product. This is displayed in the graph at right, which comes from the MIGHTY Solar study, which shows the increasing demand for a material like cobalt produced as a byproduct, extracted first from one material, and then when the extraction is optimized from that material, the market for the dominant material is inelastic with respect to the demand for the byproduct. So a new material has to be brought online with a learning curve and its own eventual saturation, followed eventually by another material, and finally by primary extraction of the rare material, in this case, cobalt. All of these changes from one co-production or byproduction scheme to another generate fluctuations and risk in the supply of the rare material. Finally, some comments on nickel. Nickel is the most mature technology. The range of historical CAGRs shown here on the left is particularly narrow for nickel, reflecting a stable and mature market. Rapid expansion needed for large-scale NMC deployment, therefore, is particularly challenging. For example, to produce 100 terawatts of NMC batteries in either the 811 or 622 chemical configurations by 2050, assuming 25% of nickel is used for battery production, would require a compound annual growth rate over the next 30 years that's 3 times the highest compound annual growth rate for nickel that has been observed over the past 50 years. There's strong demand for nickel for stainless steel, which now takes 68% of produced nickel, and other alloys, which would compete with increasing demand for batteries. As already mentioned, nickel is now produced primarily as ferronickel, a nickel-iron mixture, which is unsuitable for use in batteries. Batteries now require nickel produced from sulfate ores. Development of an efficient way, new development of an efficient way to produce battery quality nickel from ferronickel would produce significant market disruptions. Finally, as mentioned by Elsa, the long lead time from discovery to production, which was particularly significant in Elsa's graph for nickel, shown below at the right, would hamper the development of nickel resources over the timescale that's necessary for the 2050 time horizon. With that, let me stop sharing and pass the mic back to Elsa.
Thank you so much. So I think I'll just wrap up with a couple comments here so we can go to questions. Just to briefly mention a few thoughts on vanadium that was mentioned at the beginning of Bob's section. Some highlights from vanadium. It has similar sorts of characteristics to some of these other challenging minerals. The majority of vanadium comes from a focused set of geographies. South Africa, China, and Russia is 85% of the world's vanadium. And the vast majority of vanadium is currently used in steel as alloying for steel. So significant shifts in the end uses for vanadium, often presents a challenge when we have those significant shifts, as was talked about in the nickel case. There are 3 main pathways for vanadium production that's shown on the left here, the majority being co- and byproduct production in steel mills, as I said. There's also some mines that are dedicated principally by revenue to vanadium production, and also secondary sources of vanadium production, which are potentially a way in which vanadium production could grow in response to significant demand increase from vanadium flow batteries, as was talked about in the previous section. So I think in vanadium is an interesting case that reflects the comments I made at the beginning, that it's not necessarily that vanadium is scarce or is a sort of a resource running out kind of issue, but that its abundance is really confounded by highly concentrated production in geography, and the diverse nature of the supply sources that would be suitable for increase, which would be these secondary sources, which are a small percentage now. They're very very distributed, and so you know, that juxtaposition creates some challenges. The similar CAGR plots that Bob was shown in the previous examples is shown on the right for vanadium, and here the vertical black line is representing at around 10% is a upper bound on historic growth rate for vanadium. And note, please, that the x-axis of this graph is much smaller in magnitude, you know, ends at an earlier point than Bob's. And so even looking at this 10% compound annual growth that is an optimistic value, new vanadium redox flow battery deployment would be, you know, between 100 gigawatt, it would be limited by 200 terawatt in 2050, as is shown in this plot here. And we also talk about 2030 in the report as well. And so while going up to 2 terawatts would be a significant increase in redox flow batteries, that's orders of magnitude less than the 100 number that Bob was just talking about in terms of terawatt hours. So again, these sort of juxtaposition or complexities that can lead to volatility in supply chains. So we've been focused on, you know, on extraction as meeting primary demand. It's useful as we close here to reflect a bit on the role of recycling. And, you know, over the next decade, managing end-of-life batteries is going to become significant, or storage technology, I should say, is going to become significant and a requirement, we would say. But there are challenges with that demand being met in the immediate, you know, by these through secondary sources, because we have a significant increase in demand that we're coupling with products that have a lifetime. And I think this juxtaposition of plots here makes this point. On the left, I'm showing light and heavy duty electric vehicles on the market forecasted up to 2030, broke down by region geographically and whether or not they're light and heavy duty. And on the right-hand side, the corresponding electric vehicles reaching end of life. But you'll note that I've cheated here on the y-axis, order of magnitude less for the right-hand plot. And so if I, in fact, you know, shrink the y-axis to be aligned now with both the right and the left-hand side, we see that the supply of electric vehicle batteries reaching end of life, it will take some time for that to start to meet the demand because of the lifetime of the battery packs. You know, this is again focused on electric vehicles, but in order for those materials to be available for the storage technologies that we've been talking about, there's a temporal disconnect there as well. And we can think about that again as we've been doing so far. By element, and so on the left-hand side is retired again electric vehicle packs, with this idea that those materials could be potentially available for electric vehicle, grid-based storage, keeping in mind the idea of reusing those packs and secondary life as further delay for those materials being available, and then how that corresponds to elemental availability. And this idea is of the demand being significantly higher than the recycled supply of material persists throughout all of those materials that we're showing there across cobalt, lithium, manganese, and nickel until about 2040, when some of those scenarios shown by the spread of lines starts to approach you know, where demand could be met by use of those materials. And so, you know, our assertion here is that recycling is not going to contribute significantly to meeting supply now for growing deployment, exponentially growing deployment, but we need to plan for that in terms of managing the resources at end of life. And that points to the myriad research that's been being done and is done in the area of different ways in which we might cost effectively try to achieve recycling, you know, viable recycling systems for batteries, you know, and being this requirement that we manage them effectively over the next several decades becomes clear based on these different routes we might pursue, from Second Life, looking at direct recycling, which would be just lithiating those the cathode materials and using them back in batteries, versus chemical processing like hydrometallurgical processing, or heat-based processing in pyrometallurgical, that furthest outside circle. So these are aspects that we need to keep in mind, that's challenging for that supply to meet demand in the immediate, but it's something that needs to be thought of as we move forward. And to bring things back to the point that we were making in the beginning about as we transition towards a more minerals intensive future, we need to be thinking about the environmental implications of that and the associated trade-offs with processing, beneficiating, and producing the minerals that we again need in terms of moving towards low carbon technologies, in particular focusing on the storage technologies on the grid. And as we require more of these minerals, it may involve higher environmental impacts and emissions intensities. And Bob provided that finding around the scaling required. We need to more effectively manage resource extraction for energy storage. And the set of plots on this and figures on this slide just give us a sampling of that challenge. So the upper left-hand box here is looking at the carbon intensity in terms of kilograms of CO2 equivalent per kilogram of nickel extracted, comparing an average of today's emissions using today's nickel extraction technologies towards more emerging technologies that would help us meet those scales that Bob pointed out in the Kaggle plots, are upwards of several factors higher than today's nickel extraction technology. So that's one challenge in terms of the production itself. And the other challenge has to do with, as we're extracting more, we're looking to lower grades of material. So the bottom of this slide, I'm showing copper ore grade in Chile over time up until 2019, where on average we see a decline in the concentration of copper, meaning we need to dig out more rock per kilogram of copper extracted to realize the sorts of electrification that we need in order to make this transition. And of course, things like CO2 emissions and energy used in extraction are not the only kinds of environmental impacts we need to consider. As we know, several of the sources that we would be extracting these materials, as Bob alluded to, are come from particularly stressed regions. Here I'm showing a map of water stress as it relates to copper and lithium deposits, shown in the blue circles for copper and the green squares for lithium, overlaid on this intensity of water stress based on geography. And so these considerations will need to come into play. And given the point I made around recycling, we need to be thinking about the environmental sensitivity of these regions in primary extraction contexts. And that is just further exemplifying this trade-off that I made mention of at the beginning. So to summarize the points we've made here and then open up for questions, in addition to the findings from the report itself, we've also made these broader points around materials demand is going to need to grow to meet decarbonization needs broadly, but definitely specific to the storage on the grid. And then these challenges are not the same across materials. And that was brought out by the individual points that Bob made. And we need to be able to think about them specifically in mitigation strategies in a targeted way based on mineral. That we've made this point that it's not about running out, it's about matching the temporal and contextual scale needed in terms of the evolution of the technology, in terms of these delays and what's required in terms of mining operation, in terms of the challenges of recycling meeting demand in the case of exponential growth of need, and the briefly made points around these environmental impacts, both in terms of the geographic distribution of that and the challenges around byproduct production, but also more broadly the environmental issues that are inherent in material supply chains more broadly. So I'll stop sharing now and we can take some questions.
Thank you very much, Elsa and Bob. That was great, and it was interesting to watch you answer the questions as they came in real time. So some of these I think you've answered, but I may come back to a few of them to see if there's some clarification we can add at this point. So one of the early questions was relates to how material recycling and circular economy can improve the supply of critical materials needed for the energy transition. You picked a few of those, and you gave some examples of that towards the end of the presentation. Are there materials or some battery chemistries for which that's going to be more difficult than, say, you talked to lithium, for example, as a chemistry where there's good progress in the recycling? How about some of the other chemistries we might look to?
Yeah, I'll make a couple points and then definitely fill in Bob. So even within the lithium chemistries, and this point is a bit kind of relevant to the previous webinar on the technology. Sometimes the choices that we make around availability and around cost on the manufacturing of the batteries. So for example, moving towards a lithium iron phosphate as opposed to cobalt nickel based chemistries have kind of unintended economic challenges then associated with the recycling, right? As we're moving towards iron, that in a cathode chemistry, for example, or even in some of the examples that Yet gave, that means there's less value inherent to drive the recycling process, and so that's a trade-off that we see even within the lithium chemistries, but also extends beyond, right? As we're moving towards more abundant, lower cost, that means that there's less inherent incentive in recovering the materials at end of life. And so that's just a trade-off to keep in mind. One thing I only briefly mentioned that is an important part of understanding the role of recycling is the ways in which the technologies would cascade or move around to various end uses in terms of reuse, of refurbishing, and that also will vary by technology in terms of the viability of that as an approach, in terms of understanding the state of health of battery packs, or what end use is more relevant based on what the previous market end use was. And so I think those are the sorts of complexities that start to play when we think about recycling.
Okay, thank you. Bob, did you want to add anything to that?
Well, this is yeah, I'll just add emphasize a couple of things that in the case of batteries, repurposing and reuse are really distinct and other possible routes that need to be explored. The level of efficiency that's required for electric vehicles is probably higher than would be required for grid applications. So batteries that have expired their use in electric vehicles might be repurposed for grid storage, provided that there's an understanding of the long-term reliability issues. So you need not necessarily pull these batteries apart and refine them in order to make use of them.
Okay, thank you. So could you speak? I mean, it's not the recycling or circular economy per se, but the environmental impacts more generally from material choices. To the extent you recycle completely, that's not an issue, or reuse, it's not an issue. But perhaps end of life, how do you dispose of some of these materials? And does that favor some chemistries over others as we get to very, very large scales?
Quite an interesting question. Let's see. I don't know, Bob, if you have thoughts, but one thing I would say is that sometimes where there are technologies that have particular toxicity concerns or end of life disposition concerns, that can also drive policy that helps with more effective end of life management. So lead acid batteries is an example, right, where they're because of and nickel cadmium, right? So again, there's these sorts of trade-offs that are where there are acute issues that we know of and that we have designed systems around. Then we know how to have policy drive environmentally responsible behavior. For the things that are where it is less clear or where there's more ambiguity, then that often is where there can be challenges. So maybe I'm answering that in a little bit more of a meta way, but I think there are lessons to be drawn from lead acid battery recycling in terms of environmental challenges and how that's managed at end of life, that we should be thoughtful about in terms of really any of these chemistries. And I think particularly the last point you made is probably the resonant one, Bob, is at the scale that will be, right? Is that there's, there are going to be environmental challenges in disposition of end of life across all these chemistries, given the scale and given the challenge. And and having these minerals in the environment. I think, cobalt and nickel often have higher concerns than some of these other chemistries, but at the scale, it's going to be relevant across all of them. And vanadium, I guess, as well, is one where there's concerns from an environmental perspective.
Yeah, another angle on this question goes back to one of your early slides, Elsa, and that's the distribution of countries in which these minerals are extracted and processed. And that impacts discussion that's quite timely today in terms of supply chains. And where
I would emphasize that, the environmental concerns associated with extraction and beneficiation are probably dwarf the environmental concerns associated with battery disposal, not only because batteries are highly concentrated sources of interesting materials that people will continue to reprocess for their value, but also because the quality of ores the gauge of ores that are used to obtain these materials is ever decreasing. I point out that the USGS Mineral Commodities Summary recently increased the world's resources of nickel by a factor of 2, not because there were new discoveries, but because they decided that it was now possible to make use of 0.5% abundant nickel ores, whereas they used to put a cutoff at 1%. So one's talking about extracting these materials from ever poorer ore sources, and therefore ever larger amounts of mine tailings and all the problems that go with mine extraction, both environmental and social.
Okay, so
really requires management.
Yeah, so maybe a spinoff on that is getting vanadium from different sources. So there was a question about whether you've looked at getting vanadium from gasification ash from coal and petcoke. Another possibility, but I don't personally know the quality of that source or the cost of that. Is that something that been looked at as something might have a significant impact on cost volatility of vanadium?
Yep. Bob, did you want to?
I'll just add that I think one of the secondary sources of vanadium that's presently included in your list is from coal ash.
Okay.
So it's already
already in there.
It's already there.
Okay. All right.
Yeah, and that is one of the opportunities for scaling of vanadium is in those secondary sources, and definitely of interest. But the sort of economics behind that, the feasibility of that, and how that would drive supply is definitely, if that would drive supply of that secondary source, is definitely unclear.
Okay. There was a question about the discovery technologies for discovering mineral resources. Are there advances there that could lower the cost of discovery, or do we know where a lot of these minerals are? We just need to lower the cost of actually extracting and processing.
Yeah, there's a couple of aspects of that question. I think partly, so, one point I made throughout is this, it's not necessarily about running out. And as we know, it's about kind of doing that at the right pace. And so that response is inherent in that question, right? This idea of economically extractable material as the reserve is that, for these markets that are informing each other, that we're keeping pace, the sort of ability to extract economically, in developing supply, it keeps up with demand. That technology evolution is inherent in that answer. So that's one kind of general response to that. I think so there certainly is technology investment, and lithium, for example, moving towards direct extraction routes that are not requiring evaporation ponds, like happens in the brine base cases now, those will lower cost and conceivably also very much make, reinforcing Bob's point, environmental impact, right? The water stress in that particular area. So I think as we hopefully incorporate some environmental externalities in those costs, then we will need to be innovating in these methods, both on the recycling side, but also in the primary side in terms of, I think a lot of those are water driven, reducing the water demands, and particularly in brine-based settings for lithium. The other place where there is more technology discussion is in the nickel case, because of the grade for nickel that's required in batteries is of higher grade than the majority of how we extract it now. And so ways of getting to the battery grade relevant nickel from the more prevalent ores is another source of technology interest and investment, and doing so in an environmentally sensitive way is a big topic of discussion right now. So those are two examples where technology will need to drive some of the ways in which lower cost, but I would say, environmentally encompassing cost.
Yeah. Related to that response, there was a question about the cost impact on communities from mining activity. And I don't know if we're there yet in terms of doing analyses on that social cost of mining for storage materials and other materials that are needed in the energy transition. But I don't know if you could comment on the kind of the state of the art there, but maybe there's more of a to-do list than a done list at this point. But
I can recommend the MIT Environmental Solutions Initiative is going to do a conference at the beginning of September that will have virtual aspect on that topic specifically. And there's tremendous need for work in there. A lot of the challenges are, again, as I are water-based and the impacts on those communities. And so, there's definitely not, it's definitely not well quantified within these costs as we've been talking about it. And it's more, anecdotal is not the right word, but the sort of, challenges by community are significant, as Bob talked about. But, understanding what are appropriate ways to meet this demand that are also accounting for the local impacts in spades. Yeah.
Okay. And then there was a question, I think a little bit of confusion about the capacity of batteries needed by 2050. There was, I think, one of the first slides that maybe yet showed, an early slide said 100 terawatt hours for grid storage globally. And then, Bob, you pointed out from chapter 6, 100 terawatt hours for the US by 2050. Maybe it'd be worth just reiterating what's what. There was a 100 terawatt hour number in a recent McKinsey study, and I think that may be the confusion there. But Bob, if you would mind clarifying.
I think that we spent a lot of time during the study trying to achieve an understanding of this figure. I see Bob smiling. As I understand it, the goal was 100 terawatt hours of battery storage, of storage, not battery storage, but 100 terawatt hours of grid-based storage for the United States by 2050. With respect to batteries, there's a specific issue, because if you build thermal storage or you build compressed air energy storage, you do it locally, but battery materials compete across the entire world. So the demand for materials has to factor in not only the demand for that 100 terawatt hours of US storage, but also for electric vehicle storage and worldwide electric vehicle storage and stationary storage. And so those are large factors to multiply that 100 by. And a lot of us thought during much of this study in terms of a net demand for storage of the order of 1,000 terawatt hours.
you know,
Is that
I
fair?
think that's a very good point. And I think you point out the system issues here, right? There are a lot of different technologies that can be deployed today. We've talked about electrochemical storage technologies. Tomorrow we'll dive into some of these other technologies, mechanical, thermal, chemical storage technologies, and how much of the storage need you get from those other technologies, non-electrochemical, will affect the material needs. How much of the system you need to supply storage to, and how that will vary from region to region will be an important issue. So those are all, I think interesting system challenges. So that we're right at the end of the hour, and I'd like to thank you both, Elsa and Bob, for always very relevant and informative points that you make about the storage side. It's obviously an area where the challenges are just beginning. If we're to scale up as fast as we clearly need to, and at the same time do it in a way that's environmentally responsible. So thank you both, and let me thank the audience for participating, for sending in lots of interesting and relevant questions.